Hi, I'm Adolph Oliver, and this is a video clip where we talk about geometric problems that can be solved by quadratic equations. Formulas dealing with area, and there are a lot of these you should be familiar with: rectangles, squares, triangles, trapezoids, things like that, often produce quadratic equations that can be solved to find the answer to the problem. Let's look at a beginning example here. Okay. What we've got is they're referring to a rectangular painting, which is twice as long as it is wide. Now, one of the nice things to do with geometric figures is to kind of make a generic sketch of the figure to begin with. Here's a rectangle, which could represent our painting. And of course, the length is normally taken to be the long side and the width the shorter. And hopefully you remember what the formula is for the area of a rectangle. A equals length times width, L times W. Okay, well now let's get the rest of the information. Says the painting is twice as long as it is wide. Well, since it's referring back to wide, we're going to make wide dx, and then the length, okay, it's twice as long, so that would be twice x. So the length would be 2x, and the width x. Now, they tell us the area is 3,200 square inches. Well, we can start using this formula right here. Area equals 3,200. Remember that inches are units. That's what I'm putting in for the A. The L is going to be 2x. I'll put both of these in parents since they're multiplying each other. And the width is x. Okay, well, here we go. I've just substituted the information they gave us into our formula. And of course, we knew from the information if we made the width x, the length would be twice that, or 2x. Well, what do we got here? We got 3,200 equals, multiply these together, we get 2x squared. Now, I like to have my x values on the left because when we quote the final answer, we want to say x equals. So I'm going to interchange the sides here. 2x squared equals 3,200. Remember, when you interchange the sides, you don't change any of the signs. You keep everything the way it is. Well, the next thing I'm going to do is I'm going to divide both sides by 2. Okay, to get rid of the 2 in front of the x squared. So I'm going to get x squared equals 1,600. Okay, well now, this we can just get with the something we'll be calling the square root method. But simply do this. How do I get the x squared unsquared? I take the square root of it. But if you take the square root of one side, you got to take the square root of the other. So here we go. And the square root of x squared is just x. Square root undoes the square. Now, square root of 1,600, if you think about this or get your calculator out and do it, turns out to be 40. So we got x equal to 40. Now, here's the thing to remember. You want to find the dimensions of the painting. Don't just stop right here at x equals 40. Okay, the width, of course, is the x value. So that is 40 inches. Okay. But the length down here is twice x. So 2 times 40 equals 80 inches. Now, the thing you want to do is check and see if this is correct. Well, if this is the length and this is the width, and we want to find the area, we know we just multiply those two together. Well, 4 times 8 is 32, and we have a couple extra zeros to add on to the end of it, so that does indeed give us the original 3,200 square inches. Okay, well, rectangular areas are a common thing that we make use of here. Here's another one. Let's see what we've got in this particular problem. Okay, let's see if we can get this to come back in focus. There it is. Okay. A napkin is 5 inches longer than it is wide. The area is 24 square inches. Well, talking about longer, that's length and wide. So you got a rectangle here again. Let's just sketch another one out. Here it goes. Okay. Yeah, not very nice and square, but there it is. There's our rectangle. And remember again, length and width. Well, a napkin is 5 inches longer than it is wide. Remember, when they refer back, whoever they refer back to, that's the guy you want to make X. So they refer to wide, which is the width. Well, make that X. Now, why does it work good doing that? Well, it's very easy to get something for the other guy. The napkin is 5 inches longer than this. Well, okay, we took the width to be X and we want it to be 5 inches longer, so we simply add 5. Okay, there we go. Now, once again, our formula is A equals length times the width. Here it is. They tell us the area is 24 square inches. Okay, we have for the length X plus 5. And for the width, we have X. Okay, so here we are in these guys. Now, what I'm going to do is multiply this in. This is distributive law. The single term is in the back, so we'll just distribute backwards. Here we go. So I get 24 equals X times X is X squared plus 5 times X, 5X. Okay, like we did before. The next thing I'm going to do here is interchange the sides. So I'll scoot over a little bit here. X squared plus 5X equals 24. Now notice, when you interchange the sides, you don't change any of the signs. But now, since this is a quadratic here, and we have an X term, then we've got to use some of our quadratic methods to be able to factor this. So the first thing we need to do is get a 0 on the right. So this 24, jump it over, and we've got X squared plus 5X. Now remember, when you jump terms across the equal sign one at a time, then you change the signs, so the plus 24 becomes minus 24, and that equals the 0 that we need to be able to get the roots when we factor this quadratic. Okay. Well, we got a nice plus 1 in front of the X squared, so we're going to be able to factor this using the good old reverse FOIL. So here it is. I want two numbers that equal 24. The minus sign in front reminds me I want their difference, okay, to also be the 5 that's in front of the center term. Well, let's see. 6 times 4, the difference is 2. 8, 3, I think will do it. 8 times 3 is 24. What's the difference between 8 and 3? 5. Okay, there we are. Those are the winners for sure. Now, that means what we're going to do now is factor this guy. And we again take a look at the sign of the last term here to see what signs we're going to use in our binomials. It's minus. So as I often say, we're going to have one each of the signs. One of them will be a plus, one will be a minus, because if you multiply a plus and a minus, that'll give you a minus. Okay, so here we go. X, and I'll just feel like putting a plus here, so I'll do that. And then X minus here, and of course remember we got the 0 on the right. Now, since the signs are different, you can't put the 8 and 3 where you want. You got to get them in the right place, but there's something easy to do that. Remember what I call the bigger game? 8 and 3, the bigger value is 8. It has to have the sign of the center term. Well, center term is positive, so the 8 has to go behind the plus wherever I put it. Where did I put the plus? Well, right here. So remember, when you first write down the plus and minus, you don't care where you put them, just make sure you got one of each. So when you play the bigger game now that you figure out where everybody has to go, the 3 has to go in the other hole, so here it is. Okay, now, of course, we know how to get the roots of a quadratic. Okay, each one of these binomials can equal 0 because their product equals 0. So what value of x makes this one equal to 0? Well, -8. What value of x makes this one equal to 0? Well, 3. Now, many times when you get both positive and negative answers in a geometric problem, one of them you definitely toss out. Remember, our x is what the width is. Can you have a width of -8 inches? I don't think so. So in geometric problems, we often toss out the minus value and work with the positive one, the 3 right here. Okay, so if x is 3, that means the width is going to be 3 inches. And down here, the length is going to be the 3 plus 5 equals 8 inches. Okay, 3 inches by 8 inches. Now, by the way, you'll notice this a fair amount. It's kind of like a curiosity. Notice we tossed out the -8, but its opposite value, +8, ended up being one of the answers in the problem. But you still had to work with the +3. That's what gave you everything correct. Now, to double check this, if we've got something that's a rectangle, the length is 8 and the width is 3, we know the area is length times width, so 8 times 3 is 24, and that's exactly what we were supposed to have in the original problem up here, 24 square inches. Okay, now, let's try another one here. We can often work problems that deal with volume if they give us one of the sides. Here's an example. A box is 4 inches high, so we know that value. The width is 6 inches shorter than the length. The volume of the box is 288 cubic inches. Remember, volumes are in cubic inches, areas are in square inches. Well, if we made a sketch of this, okay, here we go. Let's see. Sketch the box in here. Here we go. Might look like this. Remember, what you're doing is you basically got yourself a shoebox here. So let's see if I can sketch something that looks halfway decent. Okay, going across here. And then, of course, remember, the other sides which are behind, I'll put in with dots here. But there would be your shoebox. Okay, now, let's start labeling these things. The box is 4 inches high. Well, here's the height here. So we know that's 4. Okay. The width is 6 inches shorter than the length. Okay, well, they mention length at the end here. So as we've said before, it's usually easier to make the guy at the end x. Now, length is alongside. So we'd say this is x. Okay, and then the width going across here is going to be, what they say, 6 inches shorter than the length. So it's going to be x less 6 inches, or x minus 6. Okay, so they gave us the height. We set the length equal to x, and then that allowed us to make the width x minus 6. Now, how do you find the volume of a shoebox like this? The volume equals length times width times the height. Well, let's put the values in that we have here. The volume is 288 cubic inches. The length is x. I'll put all these guys in parents. The width is x minus 6. And the height is 4. Okay, well, the easiest thing to do to begin with here, and we got this 4 times the right side. Let's get rid of this 4 times before we even multiply out these guys. And so what I can do is then divide each side by 4. Here we go. Now, the 4 on the right side cancels against the 4 up here. That's why we divided by 4. What do we have over here? Well, 4 goes into 28 7 times, and that leaves 8. So I think this is 72. Now, see, what we've been able to do is knock the numbers down, which makes the rest of our calculations easier. Now, let's go back and distribute the x in here. we've got x squared minus 6x. Okay, definitely a quadratic. So what we've got to do here is move everybody to the left, but the first thing I want to do, if I move the x squared over by itself, it'd have a negative in front, and that just causes trouble. We'd have to clean that up. So instead, I'm going to interchange the sides here. X squared minus 6x equals 72. And what that does is that allows me to get the x squared over here with a plus in front, which is what's required for all of our factoring methods. Well, okay, just keep progressing along here. Okay, this is a quadratic, so the 72 has to come over. Remember, we got to get a 0 on the right side before we bother factoring all this stuff. So it's x squared minus 6x. This comes over as negative 72 equals 0. Well, there's the required 0 that we're going to need. Once we get it factored, we'll be able to play the 0 game to get the roots. Okay, well now, let's start factoring this up. Remember, real problems have real answers, so if you don't make any goofs in your calculations, this will have a good answer which will solve the problem. Okay, notice the minus here means the signs are going to be, again, one of each. So let's say I feel like going x minus this time, and then x plus, and then equals 0. The requirement, of course, is simply that you have one each of the signs. Now, we got to play the two-number game. I want two numbers multiplied together, give me 72. The minus here means difference. Remember, if this was a plus, it means sum. So we want the difference of these numbers to be 6. Okay, well, let's see. What are the possibilities here? You could make 72 by going 2 times 36, right? But the difference there is 34. You could go 3 times 24. Okay, that would give you 72. The difference is 21. Well, we're getting closer, but we got to get all the way down to 6. 4 times 18, huh? See, I doubled the 2. That meant I had to have the 36. So 4 times 18 gives me 72, but the difference is 14. Well, we're getting closer. 5 doesn't go. 6 does. 6 times, let's see, what is it? I think 12. 6 times 2 is 12, carry 1. 6 is 1, and say, yeah, okay. And guess what? We want the difference to be 6. Here's our winning combination right here. So, okay, we're all set. The two numbers we want are 6 and 12. 6 times 12 multiplies together, give me 72, and the difference between 6 and 12 is 6. Okay, well, the signs are different, so we got to play the bigger game. The 6 and the 12 is obviously the bigger one. It has to go with the sign that matches the center term, which happens to be minus. So I put the 12 behind where I put the minus. Okay, I put the minus here, so the 12 goes here. The 6 goes in the other spot. Okay, now, as is common in these geometric problems, we're going to get a positive value and a negative value. And the negative value is the one we standardly toss out here. Because if x is a side of a geometric figure, sides of geometric figures cannot be negative. Okay, if you were just doing regular integers and they weren't a geometric figure, then you wouldn't toss it out, but here we do now. Okay, what's the value of x that makes this binomial 0? Well, it looks like positive 12, huh? What's the value that makes this one 0? Looks like negative 6. Well, remember, way back up here, the x was our length. You cannot have a length of negative 6, so that means down here we're going to cross out the negative 6, and what we're going to do is use x equals 12. Okay, if that's the case, let's go back up above here, and what we'll do now is list all the values. Remember, it said find the dimensions. Don't just stop with x equals 12, because you've got to give all three of them. Okay, so if x equals 12, then that means the length is 12, and remember, it's all in inches. The width is going to be 12 minus 6, okay, and that gives you 6 inches. And of course, remember, they gave us the height, which was 4 inches. Well, okay, let's see if this works. We got to take length times width times height. 12 times 6 is 72. 72 times 4, let's see, that is 288. So yes, indeed, we are correct. Okay, well, let's look at one more now. There are many types of geometric figures, but another one you often run into here is a triangle. So let's now talk about a problem here dealing with the area of a triangle. This says a triangle has a base that is twice the height. Well, let's sketch ourselves a generic triangle. Here it is. Okay. You know the base is the bottom, and the height is the distance from the top coming all the way down. Okay. Well, the next thing you have to remember is what the formula is for the area of a triangle. Area equals 1/2 base times height. Now, if you're solving this thing algebraically, here's a nice way to kind of rearrange this formula right to begin with. See, we're dividing by 2 here. So what I'm going to do is I'm going to multiply both sides by 2. We can always do the same to both sides. And what will happen is, then that means that we're still in balance if we do the same to both sides. Well, the 2 cancels against the 2 here. Over here, there's nothing to cancel. No denominator here to cancel it against. So I get 2 times A equals B times H. That's the same as this original formula up here, but it's easier for us to work with now as we solve. So keep this little trick in mind for triangles. It's a nice one when you're dealing with area. Now, let's get the information for the problem. The triangle has a base that is twice the height. Well, notice they're referring back to height here, so we'll make that our x right here, the height. And they say the base is twice that. Well, the base is going to be 2 times x then. Now, let's put our values in here. They tell us the area is 25 square inches. So if we substitute into this improved form here, on the left I'm going to have 2 times the area, which is 25, equals the base, which is 2x, times the height, which is x. Okay, well, let's clean this up a little bit. 2 times 25 is 50, equals, well, if we take the 2x times x, we're going to end up with 2x squared. Okay, as I commonly do in something like this, let's interchange the sides to get the x on the left. So 2x squared equals 50. Remember again, when you interchange the entire sides, you don't change any of the signs. Okay, well, we got to get rid of this 2 times, so I'm going to divide both sides by 2. And so we end up with x squared equals 25. Well, you probably know what x is yourself, but officially, this is what you do. You take the square root of both sides. Here we go. Square root of x squared is x. Square root of 25 is 5. Now, officially, you know, the square root of 25 is both plus and minus 5. But since we're dealing with a geometric figure here, then we know the minus values don't work, because I can't have a triangle that has a height of minus 5. That just doesn't work. So here it is. X equals 5 is what we're going to do. So we'll say, okay, the height, okay, I'm going to just write it out here since it's a little shorter room here, equals 5, and remember inches. Okay, and the base equals 2 times the 5, so it is a total of 10 inches. Okay, well remember, here's the original formula up here for a triangle. Area equals 1/2 base times height. So if you multiply the base and height together here, we get 50 inches, and inches times inches gives me square inches. But remember, we have to take half of that, so that means it gives us an area of 25 square inches, which is exactly what we're supposed to have. Well, anyway, a lot of geometric figures dealing with areas do give you equations that you can solve with quadratics, so this is one of the areas where you'll be making good use of all the quadratic stuff that you've learned along the line. Okay.